Illustrative examples of FET biasing. We are continuing the problems on FET biasing. The idea here is, so far I have explained the theoretical background required for solving these problems. But this is to check whether we are really able to use that theory that I have developed in order to solve the problems. The problems I am dividing into two parts. The first set of problems I named it as illustrative examples because this will illustrate the concept that I have taught so far. The reason for including these problems is some problems of some concepts may not be covered in the previous question papers. So this is to illustrate, to make you to cover the entire concept. Then we will go to work out examples to see how that's going to be really asked in the exams, right? Shall we go with the illustrative problems? Problem 1, I for illustration. Calculate quiescent values of VGS, ID and VDS. All the quiescent values we have to calculate. Please remember, quiescent means it can be any DC value. Quiescent point means VDS ID. So don't confuse. Quiescent point is different. Only it is VDS and ID. If it is quiescent, it can be any value. And he has given IDSS as 5 milliamperes and VP as -4. You know, these two things belong to basically to the device. As the device changes, these values will change. So this circuit I have taken, we call this circuit as 2 battery bias. Why do I say 2 battery bias? Because here input bias, output bias. For each one circuit is used. One battery is used. So 2 volts, RS, RD, VDS and so on. Now our job is to calculate these values. Okay. Now I'll apply input KVL. VGG minus VGS, IG, so on. Where VGS is minus VGS there. Where IG is 0. And why IG is 0? Please remember once for all, IG is always 0. Okay. Why? In JFET it is 0 because input is reverse bias. In MOSFET it is 0 because input is silicon dioxide layer. So therefore either in JFET or in MOSFET, in both the cases IG is 0, VGS is -2. What is our cross check? We want to have two things. VGS should be negative. If both are negative, it should be less than BP. But the good thing is 2 is less than 4, it is satisfied. Then confidently you can go to the next step. Substitute in this equation. ID is equal to IDSS into 1 minus VGS by VP whole square. So ID is equal to 5 into 10 power minus 3, 1 minus -2 by -4 whole square will give 2.5 in 10 power minus 3. That means 2.5 milliamperes, right? And as you see this curve here, ID should be positive, VGS should be negative. VGS cannot go beyond VP, ID cannot go beyond IDSS. Then output KVL. VDD minus IDRD minus VDS 0. Substitute the ID value, you will have -5 here. This is -5, 2.5 into 10 power minus 3. You know this point here, -5, 2.5 in 10 power minus 3. This is basically, it's not going to really work because VDS should not be negative. But this happened because there is no feedback. If you give the feedback, the value of VDS will be changing, and you can see it in the next problem. But this only to illustrate the problem, but at the end we understood VDS has become negative. Problem 2. Calculate quiescent values of VGS, ID, VDS. IDSS is 5 milliamperes, VP is -4. I am giving you feedback here. And please understand, I am using a single battery here. As I told in the requirements of biasing, the first thing is single battery to reduce the cost. So VD is given here, that is drop here, VDS come, and through this it comes into the input that is acting as feedback. So let's calculate. Again follow the procedure, input KVL, output KVL, substitute in VI equation. Simply speaking, these three, input KVL, minus IGRG minus VGS minus IDRS 0. ID is, because IGRS is going to become 0, so ID is minus VGS by RS, and if you substitute in the place of ID, 5 into 1 minus VGS by VP whole square, this is the value. Wherever there is ID, you can substitute. So I am going to substitute minus VGS by RS as ID here and VGS here. As VP is minus 4, minus of minus become plus 4. If I solve the quadratic equation, I will be getting VGS as minus 1.6 and minus 9.516. Then the question comes, which one should take? We should take a negative value. But both are negative. What should we take? And we should take VGS less than VP. So both are negative. Take whichever is lesser than VP. As you know, VP is 4 volts. And this becomes 1.6 here. So VGS value is finalized. The moment the VGS value is finalized, you can go for ID minus VGS by VGS, and minus of minus become plus. 1.6 by 1 kilo becomes 1.6 milliamperes. Therefore, ID also came. Then our job is to go to output KVL and see VDD minus IDRD minus VDS RS is equal to 0. VDS is minus 20 minus 16 plus 1.6. If you see, minus 5.6 here. So we need to, by this you can understand, you have to increase RD. If you increase RD, then only there is a possibility of, or increase RDS, there is a possibility of getting positive value. Here VGS negative is accepted, but VDS negative is not accepted, but there's a procedure. Third problem. Calculate RS for zero drift drain current for problem 2. Suppose if zero drift drain current is used, how is RS value can be achieved here? What is the condition for zero drift drain current? I already told you VGS minus VP is 0.628 and VGS minus VP is here. Therefore, VGS comes in a negative way, and take that value. Once you calculate this value and ID, you can solve for RS. In fact, RS is that way. Problem 4. Calculate VGS for ID is 3 milli, for E mass enhancement mass VT is equal to 3. So what is the equation that you have? You have a standard equation for E MOSFET. ID is equal to K into VGS minus VT whole square. 3 milli, 0.2 VGS minus 3 whole square. Why? Because V threshold is given as 3 here. 3 milli, 0.2 is a K value. In fact, he gave the value there. And VGS is equal to 0.687 minus pi. Which one should we take? We should take positive. By mistake, if both are positive, we should take whichever is greater than VT. Therefore, VGS is positive value is taken a 6.87 volts. That's a problem. Calculate Q point. VP is minus 4, IDS is 5. The whole idea of this problem is we need to just show how potential divider is used. Remaining problem is same as previous. So I want to illustrate how a potential divider is used in this. Right? Let's go. Whenever you have a potential divider, you should go for Thevenin's equivalent. And V Thevenin's is VDD by RG1 into RG1 plus RG2 into RG2. That's V Thevenin's. R Thevenin's is RG1 parallel RG2. These two parallel here. Okay. Having got the Thevenin's, you have to replace this. V Thevenin's, R Thevenin's minus VGS IDRS is your input equation. And as you know, gate current is 0. You are left with only ID. This is gone. ID is V Thevenin's minus VGS by RS. Therefore, in ID is IDSS into 1 minus VGS by VP whole square. So this is V Thevenin's is 10 minus VGS by 1 kilo, 5 milli and 1 plus VGS by VP, because VP is minus 4, minus of minus become plus 4, and we need to solve it. And when you solve for this equation, you will get minus 1.908 positive 8.1, because here it is N channel. We have to take what you call negative value. Take VGS as minus 1.908 and solve for ID, and then substitute ID in output, solve for VDS. The remaining procedure is same as previous. Problem 6. Determine the following for the network: VGS Q, ID Q, VDS, VDA, VGS, VS. So this is a circuit given 16, 2 kilo, 1 mega, current is anyway 0, 2 volts here. So problem is very simple, but too many things asked here. For example, if you really say this current is 0, this is directly available across VGS, therefore VGS is minus 2, because positive here, negative. Once the VGS is minus 2, you can take that VGS and substitute and solve for ID. ID became 5.625 milli. Now what is VDS if you apply? VDD minus IDRD minus VDS 0, therefore VDS is VDD minus IDRD. VDD means 16 volts minus IDRD means 5.625 milli into 2 kilo, that becomes 4.75. So whatever is the value across VDS is same as VD, because drain voltage is same as drain to source, because there is no drop. If there is a drop, there is a difference, but because there is no resistor in the source, there is no difference. VDS is directly VD 4.75. VG is equal to VGS minus 24. And what is the source voltage? So VS is 0 here. That's the problem that we have as far as this is concerned, to calculate different values. And you can put them in a graph and achieve the graph here for different values of 5.625 and IDS by 4. You can give different values and achieve. So the highest value is VP minus 8 volts. With that minus 8 volts and 10, you can give two different values and make a smooth curve. This will become the graph. Problem 7. Calculate Q point for the network. A very nice network, very simple. VDD, RD, VGS. What do you understand from this? Since VGS is 0, this results into, since VGS is 0, what do we do? Directly ID is equal to IDSS. You know why? Because ID is equal to IDSS into 1 minus VGS by VP whole square, and VGS 0, this directly come. And whatever the IDS is given, you take that value, apply output KVL and substitute. You will get, if ID is 0, if ID is IDSS here, so VDS is VDD minus IDRD. That ID is nothing but IDSS. So what is VD? VDS. Why? Because source resistor is 0. So far VDS is nothing but VD, because source resistor is 0. This is how you can calculate the values of VDS also. Graphically you can see them. ID, IDSS, VGS, VP. This is the value. Problem 7. For the N-channel depletion MOSFET, IDSS is 6 milliamperes and VP is minus 3. Determine IDQ and VGSQ and VDS, all these three. Anyway, they don't need to say like that, because ID will never come without VGS, ID VGS cannot come with an ID, therefore the both are necessary, and only when you calculate ID you can calculate VDS. So even if they say simply calculate VDS, we need to do this first bit. So therefore without doing the first bit you cannot do the second bit. That's why you can call this problem as a linked problem also. Right. In all the FETs, ID is one problem. So keeping the ID and calculating VDS is another problem. Therefore, all the problems of biasing become automatically linked problems. So let us see what is the equation here. If it is D mass, this is the here, because he said depletion mass, we are taking the same as FET equation. ID is equal to 6 into 1 plus V by minus 3, and this is 10.67. As I told you, VGS can be a positive or negative for both modes. So that's why in a D MOSFET, VGS can be positive or negative, but it cannot be more than VP. If you go beyond VP, the current becomes 0. Now this became a potential divider again. I am applying the Thevenin's, you will get 1.5, and that Thevenin's voltage you can apply, and when you apply this you will get the VGS value there, and when VGS value is coming, because this resistor is not anywhere required. From now onwards we don't calculate R Thevenin's because current is anyway 0. What's the fun of R Thevenin's? Apply here 1.5 minus VGS minus 750, then solve. Their ID becomes VGS by RS and 2 milliamperes there. So once ID value come and VGS value came, and automatically the next thing you need is output KVL and you will get VDS. So if I take output KVL, and you will get VDD and VDS and all this, therefore VDS is VDD minus IDRS. So if you substitute that, you will get 10.1 volt. So 10.1 volt, and current is called Q point. That's how a Q point can be achieved. Problem 8. Determine VDS for the network where IDSS is 10 milli and VP is minus 4. This is a very small variety again, directly shorted. Therefore, VGS is comfortably 0 here. There is no resistor here. And when you see this symbol, this is basically what you call N MOSFET. The direction source N MOSFET, VD is equal to VGS is directly 0. When VDS 0, ID is 0. When ID is 0, VD is here again 0, because ID is directly becoming 10 milli. When VGS is 0, ID is not 0. ID is becoming 10 milli. You know why? ID is equal to IDSS into 1 minus VGS by VP. Therefore, ID is directly equal to IDSS. Therefore, whatever IDSS is given in the problem, it is directly equal. That means 10 milli. And if you substitute VDS minus IDRD, 10 milli and all this becomes 15. 20 minus 15 becomes 5. Therefore, VDS is equal to 5. Problem 10. Determine IDQ and VDSQ for the enhancement type MOSFET, where ID on is 6 milli, VGS on is 8, and V threshold is 3. This is enhancement MOSFET, because in enhancement MOSFET there is no permanent channel. When there is no permanent channel, we show it as a dotted line. We show dotted line there. So permanent channel may not be existing. Okay, you need to apply again the basic principles of Kirchhoff's laws. Some current here, some current is 0, so same current comes. So the current in this branch is not there because it is simply grounded. From here to here, there is open circuit. Open circuit means current does not flow. For enhancement MOSFET, ID is equal to K into VGS minus V threshold, and if you substitute the value, ID on by VGS on, V threshold, if you substitute, you will get this much of K. And this K you can substitute for anything in the later stages, because the FET is same, K will not change. Use that K and draw this DC row line and the signal. What is the values substituted? Using that from the output KVL, what do we say? 12 minus 2 ID minus is equal to VDS. Because you can say 12 minus the ID minus this is 0, VGS here. If you come this way, it is VGS. If you come that way, it is output. So VGS contains input, VDS contains output. So solve for VGS there, and then solve for ID as how much value is coming. So ID is 2.75, VGS is 6.4, and VDQ is VGSQ is 7.5. So these are the values that we can appreciate and achieve from the problem given. So that's the what you call illustrative example.